statistical hypothesis, we have to test that is true or false. So testing hypothesis. Testing hypothesis, the process of testing the statistical is known as testing hypothesis. The hypothesis is divided into two parts, two ways, that is simple hypothesis and composite hypothesis. What is simple hypothesis? A statistical a hypothesis is said to be simple hypothesis if it gives the total information regarding the population. Suppose H follows such that H follows normal distribution 0,1, where mu and sigma square are given. This can be considered as a simple hypothesis. And another example is H such that B follows binomial distribution. Here n, p are given. When we come to the composite hypothesis is known as the hypothesis where it does not give the total information regarding the population. Like H such that X follows n mu, 1, where mu is less than 1, less than or equal to 1. It is composite hypothesis example. So we have learned about hypothesis, statistical hypothesis, testing the hypothesis. There are two types of hypothesis that they are simple and composite hypothesis. Simple hypothesis is total information regarding the population, whereas composite is there is no total information about the population. So hypothesis is divided into two types. Null hypothesis and alternative hypothesis. Null hypothesis, any assumed statement about the population. That is the assumed statement about the population. Here, there is another definition. Any assumed hypothesis is about the parameter of the distribution is known as null hypothesis. It is denoted by capital H0. H0. Example, H0 such that lambda equals to lambda naught. This is simple null hypothesis. Second example, H0 such that lambda is not equals to lambda naught. Composite null hypothesis. Third one, for an example, there is a difference between two groups of students in their examination standard. There is a difference between two groups of students in their examination standard. This can be considered as a null hypothesis example. Another example, H0 such that there is no significant difference between weights of men height and women height. This is null hypothesis. When we come to alternative hypothesis, the complement of null hypothesis is known as alternative hypothesis, and it is denoted by H1. That is the complement of alternative the complement of null hypothesis is known as alternative hypothesis. Example, H1 says that lambda not equal to lambda naught. In null hypothesis, we have seen that lambda equals to lambda naught. Here, lambda is not equals to lambda naught. That is simple alternate hypothesis. Second example, H1 says that lambda equals to lambda naught, composite alternate hypothesis. For example, there is no difference between groups of students in their examination standard. Example, there is no difference between groups of students in their examination standard. H1, another example, H1 says that there is a significant difference between weights of men height and women height. So hypothesis is divided into two types, null hypothesis and alternate hypothesis. Null hypothesis is any assumed statement about the population, whereas alternate hypothesis is complement of null hypothesis. H0 says that mu naught, H0 says that mu x equals to mu y. That is, there is no significant difference between the population means of x and y. And another example, H1, that is mu x is not equals to mu y. That is, there is significant difference between population means and means of xy. So I want you to remember this. This is very important. Critical region and rejected region. Let new topic, critical region and rejected region. Let x1, x2, xn be the sample observation which form a sample space of values x1 to xn can be taken as n-dimensional space. can be taken as n-dimensional space. We specified some region to see whether the point falls in the region or not, or outside the region. That is, we divide the whole sample space into two disjointive regions. Those are critical region and accepted region. Like in a graph, you can take two parts, one critical region and accepted region. We have to see where the population lies. Critical region is denoted by omega, whereas the accepted region is denoted by omega naught. If the point falls in the region omega, then the assumed statement h naught is rejected. If the point falls in the omega, the assumed statement h naught is rejected. That is, the region where null hypothesis is rejected, the region where null hypothesis is rejected is known as critical region or rejected region. Okay, so we have two regions, critical and accepted. Critical region is if the point falls in the region omega, then the assumed statement h naught is rejected. That is, the region where null hypothesis is rejected is known as critical region or rejected region. About accepted region, if the point falls in the omega naught complement region, then the null hypothesis is accepted. If the point falls in omega naught, the point falls under omega naught, then null hypothesis is accepted. If the point falls in the region omega, then null hypothesis is rejected, else it is accepted. So the region where the null hypothesis is accepted is known as accepted region. Note, the size of critical region is alpha and the size of accepted region is 1 minus alpha. The size of critical region is alpha and the size of accepted region is 1 minus alpha. They are complement to each other. So the decision to accepted and rejected the null hypothesis is h naught based on the simple may not always be true. Based on the sample may not always be true. May not always be true in the population. The four possible situations arranged in a test procedure are in the given of the following data. Okay. If there are two types of error, if the error of rejecting h naught where h naught is true, that is type 1 error. There are two types of error, type 1 error and type 2 error. Type 1 error states that the error of rejecting h naught where the h naught is true is called as type 1 error. The error of rejecting h naught where the h naught is true is called the type 1 error. Type 2 error, the error of accepting h naught where the h naught is false is known as type 2 error. Type 1 error states that the error of rejecting h naught where the h naught is true. The error of rejecting h naught where the h naught is true is known as type 1 error. When we come to the type 2 error, the error of accepting h naught where the h naught is false is called as type 2 error. The probability of type 1 and type 2 error. Type 1 error is denoted by alpha. Alpha equals to probability of type 1 error. This is the formula. Please remember it. It's very important. The alpha equals to probability of type 1 error. That is probability of rejected h naught where h naught is true. The probability of rejected h naught where h naught is true or h1 is false. H naught is true or h1 is false. The probability x belongs to x lies in omega. The x lies in omega where h naught is true. It can be also written in integration form, that is alpha equals to integration omega L naught dx. L naught dx. When we come to type 2 error is denoted by beta. Beta equals to probability of type 2 error. Probability of type 2 error is accepted h naught to h1 is true or h naught is false. Here alpha is rejected h naught where H0 is true. Beta is accepted H0 where H1 is true. Here beta falls where X falls in omega naught, where X falls in omega naught to H1 is true. It can be written in the integration form also. Beta can be written in integration form also, type 2 error. Beta equals to integration omega naught L1 dx. Here x1, x2, x so on till xn be the random variables and L0 be the likelihood function of the sample observation under mu naught. L1 is also the likelihood function of the sample observation under mu1. Here the probability of alpha, here alpha type 1 error, type 2 error is 1. The probability of x falling in omega to H1 is true, plus probability of x falling in omega naught, where H1 is true, both adds up to 1. So integration omega L1 dx plus integration omega naught L1 dx equals to 1. So 1 minus integration omega naught L1 dx equals to integration omega L1 dx. Both are complement to each other. So now let's learn about the level of significance denoted by LOS. Short form is LOS, level of significance. The probability of type 1 error is known as level of significance. It is also known as size of critical region. It is also known as size of critical region. That is alpha equals to probability of type 1 error. That is alpha equals to integration omega L0 dx. Power of the test. Power of the test 1 minus beta is known as the power of the test. The value of power of the test at a parameter point is called power of the test. 1 minus beta is known as power of the test. We have to find beta and we have to subtract 1 from it. Then we will get the power of test. Power of test 1 minus beta equals to probability of x belongs to omega, where x1 is true, where h1 is true. X belongs to omega, where h1 is true. Now we will learn about the one-tailed test and two-tailed test. I want you to remember the type 1 error and type 2 error, and the formulas are most important. So please note down. If you want the PDF, I will send it, okay? So one-tailed test and two-tailed test. A test of any hypothesis where the alternate hypothesis is right-tailed is known as right-tailed test. Test of any hypothesis where the alternate hypothesis is right-tailed is known as right-tailed test and denoted by RTT, capital RTT. A test of any hypothesis where the alternate hypothesis is left-tailed is known as left-tailed test. That is, if a test is right-tailed or left-tailed, there is one-tail test. H0 such that mu is less than or equals to mu naught versus H1 such that mu is greater than mu naught, left-tail test. If H0 such that mu is less than mu naught, then it is right-tail test. In a right-tail test, the critical region lies entirely right-tailed to the sample distribution. In a graph, assume in a graph it lies entirely to the right tail of the sample distribution. In a left tail, critical region lies entirely to the left tail of the sample distribution. Lies entirely to the left of the sample distribution. When it comes to two-tailed test, a test of hypothesis where the alternate hypothesis is two-tailed is known as two-tailed test. A test of hypothesis where the alternate hypothesis is two-tailed is known as two-tailed test. Example, H0 such that mu equals to mu naught versus H0 such that mu is not equals to mu naught. That is two-tailed test. In a two-tailed test, the initial region lies entirely in the both of the tails of the distribution or sample distribution. In a two-tailed test, the initial region lies entirely in the both of the tails or the sample distribution. In a particular problem, whether one-tailed test or two-tailed test, it is to be applied which depends on the alternative hypothesis. That is, if alternative hypothesis is one-tailed, then we have to apply one-tailed test. And if the alternative hypothesis is two-tailed, then we have to apply two-tailed test. I want you to show the graph, but the camera is not running. So I will let it be there. You can see in the PDF. Now, critical value or significant value. The value of test statistic which separate the critical region and the accepted region is called the critical values of significant values. Significant values. Critical values or significant values. It depends on level of significance, alternative hypothesis. It depends on two things, level of significance or alternative hypothesis. Whether it is one-tailed or two-tailed, it depends on two, level of significance and alternative hypothesis. We have to first define this value, then we have to check it for according to the level of significance. The large samples standardized variable corresponding to the test statistics is t. Z equals to t minus expectation of t by standard error of t, which follows normal distribution 0, 1. Normal as n attains to infinity. The critical value of this test statistic of alpha percentage, that is level of significance for two-tailed test, is given by Z alpha, where Z alpha is obtained by probability of mod Z greater than Z alpha, which is equals to alpha. Z alpha is the value of total area of the critical region on both tails is alpha, since normal problem curve is symmetrical curve. So we have to know the values of Z alpha. Z alpha values are for two-tailed test, 1% Z alpha equals to 2.58, 5% Z alpha value equals to 1.96, and 10% Z alpha value equals to 1.645. For right-tailed test is Z alpha equals to at 1% Z alpha equals to 2.33, 5% is Z alpha equals to 1.645. For 10%, Z alpha value is 1.28. For left tail test, the opposite signs of the values are same for the right tail test and left tail test, whereas for left tail test, that is negative of right tail test values. So the significant or critical value of Z for a single tail test, right or left, for the level of significant alpha percent is same as the critical value of Z for a two-tail test of the LOS Z alpha. We have to remember the values so that sometimes it is given in the exam, but sometimes you have to remember. Best critical region. If a critical region of size alpha has attains the same powers of any critical region of the same size, then the critical region is known as best critical region, and the test based on best critical region are known as most powerful test. Note, the quality control of technology alpha and beta are termed as producer risk and consumer risk. Most powerful test. Let us consider the problem of testing a hypothesis. So for testing a hypothesis, we have to first define H0 and H1. H0 such that theta equals to theta naught versus H1 such that theta equals to theta 1. Definition: the critical region omega is the most powerful critical size alpha for testing. H naught such that theta equals to theta naught versus H1 such that theta equals to theta 1. The probability P follows X belongs to omega. The probability the probability X belongs to omega to H naught is true equals to integration omega L naught dx equals to alpha. And probability X belongs to omega where H1 is true is greater than or equals to probability X belongs to omega naught H1 is true for all critical regions of size alpha. Therefore, 1 minus beta is greater than equals to 1 minus beta 1. Uniformly most critical region, this is another topic, uniformly most critical region. In testing of a hypothesis H naught says that mu theta equals to theta naught versus theta H1 says that theta equals to theta 1. This is the uniformly most critical region. Definition of uniformly most critical region, that is the test of finding critical region. That is the test of finding critical region is satisfying the hypothesis or not. H1 says that theta equals to theta naught versus H naught says that theta equals to theta naught versus H1 says that theta equals to theta 1. That is with probability X belongs to omega naught to H naught is true. That is integration omega L naught dx equals to alpha. And probability X belongs to omega. Probability X belongs to omega H1 is true. Now let's learn about Neyman-Pearson lemma. This is most important question. It can be in your exam paper. So about Neyman-Pearson lemma statement, let k greater than or equals to 0 be a constant and omega be a critical region of size alpha such that critical region omega equals to X belongs to S, comma f of X comma theta 1 by f of x1 comma theta naught, which is greater than k, which can be also be written as omega equals to X belongs to S comma L1 by L naught greater than k. This is for omega, and for omega naught equals to X belongs to S comma f x comma theta 1 by f x1 comma theta naught, which is less than or equals to k. If omega is greater than k, the value of f x comma theta 1 by f x1 comma theta naught is greater than k, then for omega naught, the value of f of x comma theta 1 by f of x comma theta naught is less than or equal to k. That is omega naught equals to X belongs to S, L1 equals to L naught less than or equals to k, where L1 and L naught are likelihood functions of the sample observation, where x belongs to 0 to x belongs to x1, x2, so on till xn under h0 and h1 respectively. Hypothesis h0 and h1 respectively. Then omega is the most powerful critical region, that is 1 minus beta is greater than or equals to 1 minus beta 1. Then hypothesis is h0 such that theta equals to theta 1 versus h1 such that theta equals to theta 1. For h0, theta equals to theta 0 versus h1 theta h1 such that theta equals to theta 1. Proof. Given that PDF function is f of x comma theta, defined hypothesis h0 such that theta equals to theta 0 versus h1 such that theta equals to theta 1. Alpha equals to p such that type 1 error. I told you to remember the formulas of alpha and beta, so it is useful. Alpha equals to p alpha equals to probability of type 1 error, that is probability of rejected h0 to h0 is true. Rejected h0 slash h0 is true, where probability of x belongs to omega slash h0 is true, that is equals to integration of L0 dx, integration omega L0 dx, where omega is the lower limit. Let it be equation 1. When we come to the beta, probability of type 2 error, where probability of accepted h0 to h1 is true. Probability of x belongs to omega naught, where h1 is true, that is integration omega naught, where integration omega naught L1 dx, where omega naught is lower limit. One minus beta. What is 1 minus beta? That is powerful critical region. P, probability of rejected h0 to h1 is true. The probability of x belongs to omega, where h1 is true. Integration omega L1 dx. Let it be equation number 3. Now, critical region of size alpha 1, where alpha 1 equals to probability of type 1 error equals to probability of rejected h0 to h0 is true, equals to probability of probability of x belongs to omega, where h0 is true, that is integration omega L0 dx. These are some of the formulas. So if we equate them, we will get the Neymar Pearson lemma. It is a very big theorem, so if you see, you will get a good perspective, good knowledge about it. Else, by listening, you will get it, but if you write it down, it's better for you. So now accepted region of size beta 1, that is beta 1 equals to probability of type 2 error. Probability of type 2 error is integration omega naught L1 dx of, let it be equation number 5. 1 minus beta 1. We have defined alpha beta and 1 minus beta. Now we have to define alpha 1 beta 1, that is for accepted regions, and 1 minus beta 1. The probability of rejected h0, where h1 is true, that is integration omega 1 L1 dx. Now we have to prove that omega is the most powerful region, that is any other region having less size of alpha is not giving the same power with omega. That is, we have to prove that 1 minus beta is less than or equal to 1 minus beta. 1 minus beta 1 is less than or equal to 1 minus beta. That is the critical region power of critical region region is less than power of accepted region. Let omega equals to A union C. and omega 1 equals to B union C. Consider alpha 1 is less than alpha, that is integration of omega 1 L naught dx is less than or equals to integration omega L naught dx, that is integration B union C L naught dx, where B union C is the lower limit, is less than or equals to integration A union C L naught dx, where A union C is the lower limit. Here it can be written as integration B L naught dx plus integration C L naught dx is less than or equals to integration A L naught dx plus integration C L naught dx. We can write the union as two different ways. So when we write that, we can cancel out integration C L naught dx in both sides on both sides, and we will be left out with integration B L naught dx is less than or equals to integration A L naught dx. Multiplying both by k on both sides, we will get k integration B L naught dx is less than or equals to k integration A L naught dx. Let it be equation number 7. Now, according to the statement, L1 by L0 is greater than K. We have seen it is in the statement given above. Applying integration with respect to A on both sides for L1 by L0, which is greater than K, we will get integration A L1 greater than K integration A L0. We can write it as K integration beta L naught dx is less than or equals to K integration A L naught dx less than integration A L1 dx. That is K integration B L naught dx is less than or equals to integration A L1 dx, which is equation number 8. L1 by L naught is less than K, integrating both sides by B. Integration B L naught dx is less than or equals to K integration K into integration B L naught dx, that is integration B L1 dx is less than or equals to K into integration B L naught dx, which is less than or equals to integration A L1 dx. Here, integration B L1 dx is less than or equals to integration A L1 dx. For the final form, that is integration B L1 dx plus integration C L1 dx, adding integration integration C L1 dx on both sides, we will get integration B union C L1 dx is less than or equals to integration A union C L1 dx, which is equals to integration omega 1 L1 dx is less than or equals to omega, which is less integration B naught integration B union C L1 dx is less than or equals to integration A union C L1 dx. Integration omega 1 L1 dx is less than or equals to integration omega L1 dx, which need to be proved, and that is according to equation 6 and 3, with, 1 minus beta 1 is less than or equals to 1 minus beta. That is hence proved. This by telling this, you won't get this. If you see it once and if you practice it once, it is a good move. So for that, I think you have the PDF. Practice from that. It is very important question. Okay, I think the time is up. I'm going to close the session. Thank you. Any doubts, Nilofer?
No, sir, no.
Okay, thank you. What was the name of the other guy who joined? I forgot to take the screenshot. Nilofer, do you remember the other guy?
No, sir.
Okay. Okay, time is up. You can leave the session. Thank you.
Okay, sir.